Hello everyone, this is Vikas pursuing MTech from IIT Hyderabad. Today I am going to present about my project titled Design of SRAM-based XOR full adder for in-memory computing done as a part of the course of Neuromorphic Devices for AI and ML under the guidance of Dr. Shubhadeep, and these are my team members Ram Mohan and Sriram. Coming to the introduction of my project, as we all know, the current boom in the technologies AI, ML, and big data, which requires huge computing and high-speed computation. And the traditional von Neumann architectures will have the memory and logic as separated and connected by the databases, which increase the latency and power consumption, which we also call as the memory wall. And to address that issue, what we think is like, can't we do the computation, small amount of computation in the storage cells itself? This leads to the in-memory computing. And for that we also know that the all the operations in the current generations current technology is doing in the complete digital format, and the full adder is the fundamental basic block for every digital operation. And for the full adder, half adders are the fundamental digital blocks, and for half adder the output is sum, which is XOR by the inputs, or the XOR of the inputs and of the inputs, that is the carry. And we implemented this operation in 60, 80 and 8 plus T SRAMs and designed computation within the memory. As I already mentioned about the bottleneck and the shift of computation paradigm from logic centric to the data centric, and when we ask the question that really the computation architecture has changed, the answer is no. Still we are using the von Neumann computation architecture for doing all the current computations also. So the need for in-memory computing has arisen, and the objective is to implement the full in-memory computing operations with the full adder using the different SRAM cells, and to decrease the latency and compare the performance metrics, and do the full adder, which will give the optimized performance. And coming to the literature survey, we have done we have read many papers and listed very few of them. And the paper title XRAM enabling in-memory Boolean computations in CMOS static random access memories. This proposes some very good 8T and 8 plus T things, but the main drawback is that it requires the skewed sense amplifiers. The skewed means we are changing the metastable point of the inverter. That is very not advisable to do. And the second paper is also using the sense amplifier, which increases the area. And the third paper, this they did very well work, like with they implemented whole logic operations and implemented a half adder with only 4 logic gates, but they used 4 sense amplifiers, which drastically increases the area. And for high performance, this they use the 8-bit RBL and RBL bar for computing the 8 plus T SRAM, but here the main problem is they use the CMOS XOR gates, which is for computation of the full adder. But we also not that is also not advisable in memory computing. And the fifth paper, they use the again they use the skewed inverters, which I already discussed. They will play with the metastable point of the inverter. And coming to the methodology in memory, like we did we start with the memory computing of SRAM, and we designed 60, 80 and 8 plus T SRAMs in 65 nanometer technology, and then we implemented in memory computing in all the architectures and find this output sum and carry, and we compared the performance metrics and implemented the full adder in the best architecture that is observed. From now on, my friend will continue.
Hi all, myself Ram Mohan. As my friend discussed the objective to do in-memory computing, we start with 60 SRAM cell. 60 has bit length and bit number, which is common for both read and write operations. To implement logic operations in 60, we take help of two sense amplifiers. And the sense amplifier is shown here. As shown in the sense amplifier, it has two NMOS of different strengths in their pull down. One is MBL transistor and another one is MBLP transistor. In here we have NAND sense amplifier and NOR sense amplifier. In NOR sense amplifier, the bit line is connected to the strong NMOS and it will give NOR at the sense amplifier output. In NAND sense amplifier, the bit line bar is connected to strong NMOS and it will give NAND at the sense amplifier output. Before we compute XOR, the XOR bit line is pre-charged to VDD, and this is the configuration where we compute XOR operation. Although it gave the logic operations, but the problem with the 60 based implementation is it has low noise margin and read-write coupling due to shared axis path. So we move to 80 SRAM based half adder. The 80 SRAM based cell has separate read bit lane, so that it has no read write conflict, which is the reason it has high noise margin. Here this is the 80 cell architecture which is used in in-memory computing. The bit lane is connected to both the cells in common. While reading, if any cell stores 1, then the bit line which is precharged to VDD will now discharge to ground and vice versa. Here the RBL gives wired NOR of 2 cells. This is the RBL which I am talking about. To obtain AND, RWL pulse timing is so important. It is short such that the pulse is very short such that the bit line in case of 0 1 and 1 0, it will not discharge completely. It discharges only in case of 1 1. For AND operation, we skewed the inverter by making the pull down of the inverter uh, strong such that the output is 0 except for the case 1 1. Similarly, using two balanced inverters connected as buffer, which is connected to this RBL, we will get NOR at the output of the buffer. And the XOR operation, uh, we will get the XOR operation by NOR of NOR here and the AND here. But due to the skewing of this inverter, 80 SRAM is sensitive to noise.
Hello everyone, this is Sriram. Till now you have seen the half adder implementation using 60 and 80. In 60 we need sequential pulsing and also there is sense amplifier area overhead. And when it comes to 80, you know that there is a skewing of inverters which is making the circuit prone to noise. So now we try to move to 8 plus T SRAM based half adder. In 8 plus T SRAM, here we have two pair of complementary bit lines, both for read and write. So when the cell stores a voltage 1 inside the cell and read enable is given, the corresponding bit line is discharged to 0. So that when two SRAM cells are connected to the same pair of bit lines, the NOR operation is brought on RBL and AND operation is brought on RBL. In the further next slides, you will see how sum and carry are implemented. So here you can see this is the 8 plus T cell and this is the another 8 plus T cell. This is the tail transistor which will sense this read enable signal at its gate. And similar fashion in how we did XOR in 60, here also from RBL and RBL bar you will be getting this XOR operation. This is the truth table for half adder implementation using 8 plus T. Now, since we have implemented successfully the half adder, to implement the full adder, we just need to transfer this XOR computed into a new 8 plus T SRAM cell. For this, we are requiring a MUX which will convert or transport this XOR implemented in stage 1 to the new 8 plus T SRAM cell. We need a select line which will decide the functioning of the new cell as cache memory or for the purpose of this computation. Then next, the next pair of bit lines RBL2 and RBL bar 2 will compute the sum for our full adder. You can see the architecture in the next slide. Here, as you can see, we implemented this AX or B, NOR C and AX or B and C on RBL2 and RBL bar 2, and NORing these two we will get the final sum output. And for carry output, we use this consensus theorem of Boolean algebra and implemented it using this pass transistor logic in order to minimize the number of transistors as well as power. So this is the truth table where you can find all the bit line conditions like RBL1 will give you the NOR operation, RBL bar will give you and so on. And finally sum is calculated by NORing this RBL2 and RBL bar 2, and carry is computed using the RBL2 and as well as RBL bar 1. Thank you.
I think till now you enjoyed, understood, and able to appreciate our implementations. Let's look about the results. Let's start with the noise margins, comparison of noise margins. A noise margin for 60 and 8 plus T cell. We'll draw the butterfly curves using Q and Q bar, and we'll compute the noise margin like if this, you can see here, this is the point, this length is of around x width, and this x width comprises of 0.2 volts, and if this length width is of around y volts, then what would be the thing? It's simple math equations, and when we do that, we'll get the noise margin of 60 as 0.143 volts and noise margin of 8 plus T as 0.267 volts. And plots for the 60 SRAM based half adder, I think my friend had clearly explained about the implementation and architecture. Now let's start the analyzing the curves. First, the bit line will be precharged to VDD, and the respective voltages, like which one we need to write, and then the word line will be asserted, and the thing will be like what we want to write will be written in the cell, and then again we will precharge to VDD, and for the read operation we'll apply very small pulse here, the skimming pulse, like which my friend had already explained, I think so. And these pulses will give very short, not to disturb the values whichever on the cells, and are bit lines. Then you can see these we have computed, and we check the things like for 0 0 the sum and carry would be 0, and so on the case till 1 1. And from now my friend will again continue.
Now we will see the plots for 80 SRAM based half adder. As shown in the results, the half adder is correctly implemented, which is XOR operation and AND operation, which represents carry operation in 80 SRAM. For each case, for each possibility, we plotted the sum and the carry, and the average power we got is 85.69 microwatts, and the latencies is also mentioned in the results. And we also plot done layout for 60 cell. We have used metal 1 for word lane, which runs as row, metal 2 used for bit lane, which is a column layer. We got an area of 32.4 micrometer square, and for 8 plus T we got an area of 47.7 micrometer square, which is 50% more compared to 6T. Now we will see the latency, area and power comparisons of 60 versus 8 plus T. The latency was decreased by 5 times for 8 plus T compared to 60, and area is increased by 50%. For 60, the average power is 381, which is very larger compared to 8 plus T, which has 62.8 microwatts.
From the previous slide, you must have understood why we used 8 plus T SRAM cell. So now this is our simulations done for 8 plus T SRAM cell half adder. We have taken the 4 cases 0 0, 0 1, 1 0 and 1 1, and for first 350 picoseconds we precharged the bit lines, and then computed our logic operations. You can see all the logic operations are perfectly implemented. 0 for the 0 0 case, 0 1 and 1 0 and 1 1 case. So next, this is the complete schematic of full adder using 8 plus T SRAM cell. This you can consider as one half adder. This one you can consider as one half adder. This is the XOR circuit, and this you will get the past ancestral logic for final carry output, and this is the final sum output schematic. So now for the full adder using 8 plus T, around 700 picoseconds you will be getting the logic operations, and all the cases have successfully done the correct computation values. Like you can see, all the notations are given here for sum and carry for each case. Here from the mux output, writing into the fourth cell is given by this yellow color schematic. Next, these are our biasing voltages given to the full adder. Like these include pre-charge signal given to the XOR or bit lines, and these are the word lines given to 1 and 2 cells. These are the third and fourth SRAM cells word lines. These are our inputs which are to be stored into the SRAM cells. This is the mux output. These are the read enable signals which will help us to compute the XOR operations. So now we try to check if our system is robust to check variance in the capacitance of bit lines. We did 10% variations in read bit lines capacitances, and successfully the system is found robust with 10% variation also. Next, we have simulated for different process corners, SS, FF and TT, and we have taken the temperature range from -25 to 85, and the schematic was working well for all these PVT variations. Now, for the average power of our full adder, it was around 0.39 nanoseconds for sum and 0.38 nanoseconds for carry. And the total power for full adder computation, it was around the average power was around 201 microwatt. So in order to go concluding this our project work, here we designed the half adder using 60, 80, 8 plus T, and then choose 8 plus T for implementation of full adder. Even though the area is less in 60, there is read-write coupling, sequential word line enabling. All these are drawbacks of 60. The latency is also worst case of half adder, around 5 to 6 times more than 8 plus T. Also the 8 plus T is working faster. We observed that the average power for half adder implementation in 60 is much higher than full adder implementation in 8 plus T. So we concluded that 8 plus T is the better in terms of power, performance, and area. Like in area we compromised a little bit, but in cache memories we need the fastness and low power. So 8 plus T is the best in all terms. The future work include this 1-bit full adder to be extended into an n-bit full adder, and then followed by implementing multipliers. So these are our references which we read and took the ideas. Thank you.